Hello students, we are studying Internet Protocol Security, and in that the last topic is Oakley Protocol. So yesterday in the previous video we have seen that Internet Key Exchange Protocol is required whenever there is the security association is not established between the two parties. So for that we require the Internet Key Exchange Protocol, which is responsible for generation of security association. In that, one of the protocol, which was ISA-KMP protocol, which we have seen in the previous video. Then this video will study about the Oakley protocol. So Oakley protocol is basically, it is a key determination protocol and it is based on the Diffie-Hellman key exchange algorithm, which we have already studied in the previous unit. So as we all know that the key establishment or determination of a symmetric session key between the two entities is the heart of data protection that relies on a cryptographic technique, and it is an essential component of the packet protection. So therefore, there is a strong need of scalable and secure key distribution mechanism for the security. So the goal of this Oakley protocol is to provide that mechanism of key determination, and it is coupled with a great deal of cryptographic strength. The Diffie-Hellman key exchange protocol provides such kind of mechanism. It allows two parties to agree on a shared value without requiring the encryption. And the shared value is immediately available for the use in encrypting subsequent conversation. So we have already studied in detail about how the Diffie-Hellman key exchange protocol is responsible for generation of symmetric session key. So here the Oakley protocol is the advancement of Diffie-Hellman protocol, and it is used to establish a share key with an assigned identifier and associated authenticated identities for the two parties. The name of the key can be used later to derive the security association for the authentication header and encapsulation security payload protocol, or to achieve the other network security goals. So each key is associated with the algorithms that are used for authentication, privacy, and one-way function, that is a hash function. So these are the ancillary algorithms for Oakley protocol, and their appearance in the subsequent security association definition derives with other protocol is neither required and nor it is prohibited. So Oakley is basically designed to provide the compatible component of ISA-KMP protocol, which runs over the UDP protocol using a well-known port number. So it is a specific key exchange algorithm which is required for use with the initial version of ISA-KMP. Now let us look into the features of Oakley protocol. So this Oakley protocol is related to STS, that is sharing the similarity of authenticating the Diffie-Hellman exponentials and using them for determining a shared secret key, and also of achieving the perfect forward secrecy for the share key, but it differs from STS, that is sharing the similarity protocol, in different ways. So what are the features of Oakley? The first one is it employs the cookies to thwart a clogging attack. So clogging is nothing but a denial of service attack. So the first is the addition of weak address validation mechanisms, and cookies can be used to help avoid the denial of service attack. So anti-clogging tokens or cookies, they can provide a weak form of source address identification for both the communicating parties. The cookies can be completed before the exchange of the cookies can be done before the perform the computationally expensive part of the protocol, that is exchanging of exponents. So it is important to remember here that the Oakley protocol uses cookies for two purposes. First is for anti-clogging, that is to stop the denial of service attack, and the second one is key naming. The two parties to the protocol each contribute one cookie at the initiation of the key establishment, and the pair of cookies then becomes the key identifier. So that we'll see later on. Then another feature of Oakley is that it allows the two parties to select mutually agreeable supporting algorithms for the protocol. the encryption method, the key derivation methods, and the authentication method. Thirdly, the authentication does not depend on encryption using the Diffie-Hellman exponentials. Instead of that, the authentication validates the blinding of the exponentials to the identities of the parties. The protocol does not require two parties to compute the shared exponentials prior to their authentication. Then this protocol adds the additional security to the derivation of keys which are meant for use with encryption by including the dependence on the additional algorithm. Then the derivation of the keys for encryption is made to depend not only on the Diffie-Hellman algorithm but also on the cryptographic method used to securely authenticate the communicating parties to each other. Then finally, the protocol explicitly defines how the two parties can select the mathematical structure for performing the Diffie-Hellman algorithm. Then they can use the standard group or define their own groups. And user-defined groups can then provide the additional degree of long-term security. And then the authentication mechanisms which we are using here in the Oakley protocol can be used to thwart the man in the middle attack. For the Diffie-Hellman protocol which we have seen was susceptible to man in the middle attack protocol, man in the middle attack. But whereas here in the Oakley, we are providing the authentications in such a way that it is secure from the man in the middle attack. Now let us understand the message descriptions in the Oakley protocol. So there are two parties, initiator and responder. The one which we have seen in the Diffie-Hellman protocol was the two communicating parties, Alice and Bob. So one is initiator and the other one is responder here. The arrow is indicating whether the message is sent from initiator to responder or vice versa. The fields in the message are named and they are comma separated. The protocol uses the convention that the first several field constitutes a fixed header format for all messages. For example, consider that the hypothetical exchange of messages involving the fixed format message. The four fixed field being two fields are cookies. The third field is being a message type name. The fourth field being the multi-precision integer representing the power of the number. So there are four fields in every message. So the notation describes the two message sequence. The initiator begins by sending a message with four fields to the responder. See this first message, which is going from initiator to responder. The first field has the unspecified value, that is cookie I, which is the cookie of initiator, which is nothing but some random number. The second field has the numeric value 0. The third field indicating the message type is OK key X. The fourth value is an abstract group element G to the X the power, where G is the generator as we have seen and X is any random number which is selected by the initiator. Then the second message is going from responder to the initiator. It indicates that the responder replies with the value cookie R. That is nothing but the responder's cookie, that is responder's random number. So the first field is the cookie R, the copy of cookie I value which is received in the previous message by the responder. Then the message type OK key X and the number G raised to the yth power. So the value OK key X is in the capitals to indicate that it is the unique constants. So constants are defined here in appendix. These are the constants. Then the variable precision integers with the length 0 are nothing but the null values for the protocol. So see here in the first message, the 0 is indicating that initiator I is not having any initiator I is not knowing about the cookie of responder. So in the second message, it is sent from responder to initiator.